Hey, so I think you should be seeing my screen, I hope. Not good. Okay, so welcome officially to Serverless Workshop, second edition. We have several workshops we did in past. This is the online only workshop. Everybody should have access to Discord and be able to ask questions or have any discussions in background. We also have a mailing list. If you are not on it, please subscribe to it. And we will have another workshop together with middleware at the end of the year, and we will have soon call for papers, and expected, submission deadline is end of September. And we are looking forward to do additional workshops, and we are looking for your ideas or, how we can make it faster, easier to exchange and essentially work together. So why we are doing that workshop? Fundamentally, we think that serverless is changing, and it is not only about running function as a service. And in particular, the approach to building software and then running it that serverless made popular is gaining traction. Like a lot of services now in cloud are renamed to be serverless. And what is interesting is how to take the serverless experience and make it work everywhere that you want to run your code, edge computing with AI, essentially expand or make it easier to build software. That's why we're calling like future serverless or next gen technologies. And then the way that we organize this workshop, we ask everybody to fit into 10 minutes for their presentations. You are, as a presenter, it's up to you how you are going to use the time. If you want to have questions, leave some time for questions. And we will, before your talk ends, 1 minute before, we will do one quack sound, you will hear it. And then just about when your time slot is finishing, there will be 2 quack sounds, or, you can already finish, we do not need to notify you. So the next speaker have enough time to, start sharing and go to the next, like switch the presenter. To ask questions, please use Discord, but also if the presenter left time, use that Zoom function, raise hand. If there are, more than one questions, it's easy then to queue together. And Pedro will be talking about online polls. So that's one way that we want to engage you in the workshop to have some interactions. And it is live workshop, so take advantage of it. Pedro, do you want to switch to your screen and do polls?
Yes, I can, of course, share my screen. Okay, so let me go for it. Okay, so now you should see my screen. I will share now in Discord the link to the, to the first poll. This is a poll we already did in the previous, I can also share it here in the chat in Zoom. And this poll, we already did it in the previous one, in the previous edition. So we have the same questions. The first one is, what are the main challenges in serverless computing? So I think you can start voting here. Okay, we start to have some questions, some answers from the public.
Yeah, and the link is in the chat, Zoom chat.
Yes, in Discord and in Zoom. So connect here and okay, we see more people. Okay, if you repeat one of the existing ones, it will get bigger. Okay. Security. We will share this plot in the end, and we will compare to the previous edition. So we are seeing some interesting challenges here. from the public, like latency, programming abstractions, user experience. So we can give like a 1 or 2 minutes so people can contribute. Okay. So probably we can stop here. No, we have more answers, 25, 28, 31. Programming abstractions, latency, and state continue to be interesting problems. Yes, and low latency, like fast function as a service is still a big challenge. Okay. So I think that we can move on. 33 answers, 1 minute. And okay, I think that's enough. 33 answers is interesting. So if we don't have more answers, we can move to the second question. Also, we asked the same one in WoSCX1, and I will show you the results of the first one. So now, what is the future of serverless computing? Okay, fast one. Serverless GPT. Okay, we'll give a little bit more time because we have 30 answers in the first question. Okay, it seems that people they are thinking, so we give 1 or 2 minutes for the last answers.
So I will test quack sound. Okay.
Working perfectly.
So that's,
Then, Alex, do you think we should move to the next session?
Yes. So you can continue, right? Voting on that poll.
Okay.
And we will have more polls and continue also in Discord, right? So, okay. So I think we are ready to start and our actual presentation. I think the first one is streams under test, right? Or no, sorry, that's tomorrow. No. Sorry.
No.
Surprise. Scalable and secure serverless, right? Rodrigo, you should be able to present.
Hello. Right, I'll just start this sharing screen.
Now we'll be starting timer. You have 10 minutes.
Okay, so hi everyone. So I'm Rodrigo. I'm a assistant professor from the University of Lisbon and also senior researcher at the NSKD in Lisbon. And in this talk, I'll just get the Zoom window out of the way. In this talk, I'll go over some of the work that we have been doing on secure and scalable serverless runtimes. So serverless, when I talk about serverless, always it comes to my mind is its promise for high elasticity, for pay for the resources that you actually use, and for this very easy hands-off infrastructure management. And serverless has been quite popular so far. And if you look, in particular, one of the traces that are available, trace that was published in a paper in ETC 2020, we see that there is quite a lot of invocations per second in general. But once we zoom into the number of invocations for a particular function, we see that this number drops quite a bit. In particular, many functions are not even invoked, not even once per minute. So it means that for a single function, we might need to wait several minutes until we see another invocation to the same function. And in practice, what this means is that the serverless platform is constantly creating new workers or new instances where these functions need to run because they are constantly changing invocations. The invocations are constantly changing in terms of the function that they are running. And this means that the virtualization technology that we have is now on the critical path. It's not that it was not on the critical path before, but it's now much more exposed because we are constantly launching these runtimes. And if you look at the virtualization stack that we have, usually we will have some kind of VM or a container. And on top of it, we will have a language runtime, something that would allow us to run JavaScript or Python or Java code. And both of these components alone, they might take dozens or even hundreds of megabytes and dozens or even hundreds of milliseconds to launch. And these not only individually are expensive, but this creates this compound overhead that we call the virtualization stack tax, where you need to wait for the VM or container to be launched in order to actually launch your language runtime. And people have realized that this is a big problem, and some solutions have been proposed. One of the most popular ones maybe is to do snapshotting, where we can basically snapshot the state of the stack and then restore it later. But still, for very lightweight functions, this still creates a high cost in terms of memory footprint and startup latency. So in this work that we are doing, we are actually investigating the possibility of providing an environment where we can launch functions, and we don't want to restrict too much the languages in which these functions can be deployed. So we want to keep access to all the popular serverless languages, namely JavaScript, Python, and Java, but we want to do it and launch an environment under 1 millisecond and 1 megabyte of memory footprint. So in order to do this, we actually took inspiration at how the evolution of virtualization systems has been going so far. And in the start, we know how to do virtualization of the hardware through VMs. We can share operating systems with containers. And now what we think is the next step is we actually need to share language runtimes as well and use some type of sandboxing technology that allows us to share a single stack, including the language runtime, operating system, and hardware. So we want to go from a situation where we have multiple stacks or multiple instances of serverless workers into a system where we have a single stack and we can have multiple sandboxes on top of it. And this is the main idea behind Graalvizor, the system that we're building. It uses memory isolates, which is a type of sandboxing that has been around for some time in language runtimes. It heavily relies on AOT compilation, and we try to avoid as much as possible JIT compilation to avoid its startup overheads. And it also has polyglot support, meaning that we can deploy functions in multiple languages, and all of these languages can co-execute inside a single runtime. So this is one example of an instance of a Graalvizor runtime. As you can see, functions, these are the yellow boxes, are the unit of deployment. We can have multiple functions inside a single runtime. Each function can have multiple invocations that are concurrently executing in a single runtime, and these are instantiated inside the isolates that enforce the isolation of inside at the execution level. And then each isolate, there will be a code cache and initial heap state that is shared across all the isolates of a particular function. These components are typically read-only, so it's safe to share them. And for additional isolation, if the function requires it, we can actually launch isolates in a sub-process that we fork from the parent process. And in this case, the code cache and the initial heap state is actually copied on writes from the host, from the parent process. So Graalvizor is basically a binary. It can be deployed on bare metal, or it can be packaged as a container image, or you can even run it inside the Firecracker VM, where it runs as the init process directly on top of Linux. So in Graalvizor, functions are registered as AOT compiled dynamic libraries. The idea is that we can compile Java directly with GraalVM native image, which is a compiler that can convert Java bytecode into an ELF binary or a dynamic library. For the JavaScript, Python, and actually all or many other dynamic languages, we take advantage of Truffle, which we encapsulate in an AOT compiled module, such that you can actually AOT compile Truffle and load it as a dynamic library as well. And we also provide a client-side library that needs to be appended to the class path. And this injects all the stuff that are necessary for Graalvizor to instantiate and call these functions inside the runtime. So with this addition to the class path of the user, it does not require actually source code changes from the user side. So actually, we are able to reduce quite a lot the memory footprint as a startup latency required to launch one of these execution environments. Actually, we launch in less than half a megabyte and less than half a millisecond in terms of latency. When we compare to OpenWhisk, one of the most popular serverless infrastructures, we can reduce up to 49% when we're playing a trace, part of the trace of serverless in the wild. So now the next question that we're currently looking for is, well, we can actually collocate multiple functions on the same user. What can actually be done if we want to collocate functions across users or across tenants? And the question turns into is whether or not software fault isolation is enough. And in principle, it should be enough as long as functions are actually developed entirely in some managed language, because as managed language are built, the compiler and the language runtime will automatically enforce isolation. The problem is that most of these applications, or in many cases, these programs actually depend on native dependencies, and this can be for a number of reasons. And in this case, SFI is definitely not enough, because the guarantees provided by the language runtime do not extend to native code. People have been posing and have using memory protection keys as a way to isolate functions together with their libraries inside domains. But the problem is still that MPK is limited to 16 domains, which severely limits the scalability of this approach. One insight that we're trying to take advantage of in this work is that hardware isolation is only necessary when we actually run native code. And we can actually combine the isolation provided by the runtime with isolation provided by the hardware to achieve higher scalability. When we actually look at how long and how many times functions run in native code versus managed code, we see that although static analysis would show that we can actually reach native code by looking at the code of an application, at runtime, it's extremely rare the situations where we actually run native code that is brought with the user code, right? This usually happens if the user code triggers some native code, but it needs to go through the runtime and call some native code that is provided by the runtime and therefore controlled by the provider. So this is actually what we are trying to leverage here, which is transitions from managed to native code are extremely rare, and maybe we can actually share MPK domains in a way that we can take better advantage and we can maximize the utilization of these 16 domains that are currently available. So there are a number of other interesting challenges that I don't have time to go over here, but I would be super interested in discussing them offline, such as how to address problems with the scalability of namespaces and C groups. How can we go around the rates of allocation of these resources in the kernel, how to enforce kernel level isolation, and how to overcome this limitation of 16 domains, even if we hit situations where scalability is a problem. So finally, I want to thank all the people that have been involved in this project so far and leave this my contacts, and happy to take any questions or continue discussion offline. Thank you.
Thanks a lot, Rodrigo. Really cool presentation. I mean, your work in your advisor is amazing. Thanks for this presentation. But questions offline in Discord, because we have a super intense program today. So contact Rodrigo offline, because his research is super interesting. So now the second talk is Eduard Marin. Eduard Marin, he's a researcher in Telefónica, and he's doing super interesting things in security. And I think that this topic, serverless computing, a security perspective, it's new to our community and will be super. So go ahead, Eduard, and you can start.
Okay, so thanks a lot for the introduction. So in this talk, my main objective will be to talk about the security problems and challenges in serverless computing. So for this, I will first give a brief introduction about serverless, and then I will jump into the security aspects of it. So serverless is, as you all know, emerging as a new computing paradigm for the deployment of applications in the cloud. I mean, you all know that serverless doesn't mean that there are no servers, but rather that software developers don't need to think about them. I would say that serverless has three main advantages. The first one is that it allows software developers to outsource all infrastructure management and operational tasks to the cloud providers, which makes it possible for software developers to focus only on writing the logic for their applications. The second advantage is that it follows a pure pay-per-use I'm trying to find the word, sorry. It follows a pay-per-use model where users basically pay for what they use. And the third one is that it brings out scaling to the next level by allowing to scale in and out depending on the needs of the application, right? So currently, there are two main flavors of serverless. There's backend as a service. There's also function as a service. In the rest of my talk, I will focus on function as a service, as this is the most dominant serverless model today. Okay, so FAS proposes to decouple computation from storage, right? So with FAS, the application is divided into a small set of small, short-lived, stateless functions that are executed in response of different types of external and internal events that the application owner specify. And then the cloud providers also make available various types of services so that they can increase the functionality of their serverless functions. So in terms of security, at first sight, one could think that serverless computing is more secure than its predecessors because of characteristics, right? So I will talk more about this later. However, I would like you to keep in mind that serverless security is not all roses, since it brings many new, I would say, quite unique challenges that today are not yet fully understood. Okay, so one important aspect that I would always like to highlight is that serverless security requires a major change in the mindset of software developers, right? So software developers need to think about securing their serverless workloads differently, right? And this is, I would say, mostly because of this this sharing of the responsibility of securing these workloads. No, so in serverless, we like to talk about security being a shared responsibility. So we typically distinguish between security of the cloud and security in the cloud. Security of the cloud is the responsibility of the cloud providers and encompasses all the measures in place to keep the underlying infrastructure and the cloud services secure from adversaries. And security in the cloud is instead the responsibility of the software developers. And it basically includes all those security mechanisms to protect the individual functions, the data that they use, and also the workflows where they belong. Okay. So knowing all these, what I would like you to remember most from that slide is that security and privacy should be considered by design and also taken into account in all the stages of a function, from their development to their execution. So the way you write functions has an effect on the security. Clearly, the way you place the functions into the different servers also can affect security quite drastically. and obviously the way you execute them. So if you execute them inside one sandbox or another, that has an effect on security. If you choose to run them inside a TE, that of course has some advantages, but it also opens the door for other types of attacks. So next, I would like to talk about several positive and negative aspects of serverless when it comes to security. So I'll start with the positive ones. So here I wrote functions are stateless, short-lived, and single purpose. I mean, the fact that serverless functions have small code footprints, are stateless and short-lived, makes it much harder for adversaries to perform attacks successfully. Okay, so with serverless, long-standing servers don't exist, meaning that adversaries need to carry out their attacks again and again, including this phase where the adversary is trying to collect information to perform the attack, which basically increases the cost of the attack and makes it easier to detect the attack, right? So it makes the attacks less stealthy. Then also by using small single-purpose functions to realize those applications, the application owners can define more fine-grained security policies and reduce the impact of attacks. If one of these functions is compromised, adversaries are limited to exploiting the capabilities of a single function. Okay. And then also, due to the way serverless functions are designed, not all serverless functions need to send the results back to the internet, okay? Which means that we can hamper adversaries from conducting certain types of attacks. So now, for example, attacks to exfiltrate data become a bit more challenging. One needs to find other ways to exfiltrate data. It's not as simple as sending it over a server that is connected to the internet. Another important aspect that is, in my opinion, very positive is that security is a shared responsibility between the software developers and the cloud providers. So here, it's quite obvious within the security community that delegating all the infrastructure-related security tasks to the cloud providers is a very effective mechanism to get rid of a quite important number of attacks. Okay, so providing, maintaining, and operating an infrastructure that is secure by design is actually the core business of those cloud providers. No? And then we can sort of assume that they will devote significant efforts in achieving this. Then another important point that is also very positive that I would like to highlight is that serverless by nature, by construction, can easily adapt to workload changes by provisioning and deprovisioning resources, and therefore it offers a very natural type of protection against DOS attacks. Okay. So let's now jump into the negative aspects of it. So serverless exposes a significantly larger attack surface compared to its predecessors for three main reasons. As functions are stateless and are all intended to perform a single task, they are required to constantly interact with other functions and shared cloud services. The problem here is that defining and enforcing security policies in such dynamic and complex environments is a very complex task, and it's prone to errors. Okay. The second point I like to make is that functions now can be, as you all know, can be triggered by many different types of internal and external events, each of them with their own formats and encodings, right? And we know that the trend is always to try to increase the number of events that are supported so that more applications can benefit from serverless. The problem with all this is that all these events come with their own APIs, and basically this creates a lot of new entry points for adversaries to gain control of functions. And finally, serverless platforms include a number of new components and cloud services, many of which are shared across users. These shared components are always introducing new problems when it comes to side channel attacks or covert channels. So sharing is not caring, sharing is making things insecure, and we also need to be very careful and pay a lot of attention to those components that are shared. Then there's another very interesting point that comes with a very interesting trade-off here. No? So it's quite obvious that cloud providers ideally would like to develop serverless platforms that jointly maximize security and performance, while of course, maximizing their revenue and keeping the cost for the customers as low as possible. Right? But these dimensions are in conflict with each other. And unfortunately, as you can imagine, security is the one that is often sacrificed. So for example, think about the selection of the execution environment where the serverless functions run, right? So this has a clear effect on the security that one can achieve, but also on the performance, right? We can go from traditional VMs to containers, and now even more recently to lighter types of containers. Each of them offer a different level of security, and they also come with a different types of overhead, right? Another example is the usage of warm containers, right? So the usage of warm containers are known to reduce the startup of functions, they improve efficiency, but reusing a container multiple times have been shown to be one possible way for adversaries to perform attacks, right? So this comes at the expense of providing fewer security guarantees. Also think about the algorithms for placing serverless functions. From a performance point of view, you would like to do this in a deterministic way, using a deterministic placing algorithm, right? But the fact that it's deterministic would also mean that adversaries can guess where certain serverless function will go and can try to leverage this knowledge to perform some attacks that require collocation. Instead, randomized scheduling algorithms are not so good in terms of performance, but at the same time, they offer better protection when it comes to security attacks. The last point I would like to highlight is about the backends of the cloud providers. So in serverless, as I mentioned before, cloud providers are largely responsible for providing security, which is in general a very good aspect, a very good thing. But I think that this can provide a false sense of security to the software developers. So this may lead software developers to ignore the security of their applications or unrealistic assumptions about the security mechanisms in place. Okay. Despite cloud providers being responsible for security being a very positive thing, currently what we've seen in research is that there is not much information about how the backends work. So cloud providers typically keep this information confidential, or at least they don't fully document how it works. And when it comes to security, this is very problematic, because if we don't know how it works, it's very hard for security experts to scrutinize the security of these platforms, these backends. So with this, I would like to conclude my presentation by saying that with the rise in the number of attacks in the cloud, I think that security and privacy will be crucial for the widespread adoption of serverless computing. We're currently very actively working on this from the perspective of finding new types of attacks and devising effective and efficient countermeasures. We, some time ago, we published a magazine paper where we try to illuminate, I would say, the attack surface in serverless. We explained some possible research directions, and now we're working on them. So thanks a lot. And if you have any questions, I'll be happy to take them.
Thanks a lot, Eduardo. They were asking you in the chat to copy the link of your paper in Discord or in the chat. And well, thanks a lot. So we move to the next presentation.
Thank you.
Then now we have, so you can ask Eduardo offline, so in Discord. So next one is Mohammad Sadat. He's professor in the University of British Columbia, and the title is really interesting. He's envisioning the future multi-cloud serverless, introducing a system for efficient serverless function offloading. So go ahead, Mohammad.
Wonderful. Do you see my screen, Pedro?
Yes, yes.
Great. Well, hi, everyone. It's good to be here, and I see a lot of familiar names and some new folks, so I look forward to hanging out with you. I'm Mohammed. I'm a professor at UBC, and I'm going to talk about some of our work about multi-cloud serverless and some of our recent work, how actually we can get there. You're all experts, I assume, being in this call, so I'm not going to get into details of why serverless is good, but we all know the premise is to make it easier for developers to build and deploy scalable applications on the cloud. Yet there are many challenges right now. As we speak, serverless is not quite serverless. Oops, sorry. Reasoning about boundaries of functions can be a pain. It's up to the developer to decide how to build these different function boundaries in their application. Right sizing is the main challenge. Right now, many of the serverless systems, you have to go and manually set the memory and other configuration. That's not serverless to me. And efficient data sharing is a pain, especially if you have data that has to be shared across different replicas of the same function. Meaningful SLAs do not exist. By the way, these are all ideas. If you're PhD students in this area, these are all ideas to go work on. And of course, today I'm going to talk about dealing with vendor lock-in, right? And that deals with the situation of you building a serverless application for one cloud and not being able to easily migrate it to another cloud or deploy it at the same time to multiple clouds. So a few years back, we wrote this vision paper at SOC, which talked about the merits and viability of multi-cloud serverless. And in the context here, concurrent work from Berkeley, they talked about the vision of sky computing, right? So at that time, the community was starting to think about how we can actually raise the level of abstraction beyond just one cloud. And that makes a lot of sense because as we are adding more and more options to each cloud, you have 300 options for picking different virtual machines, right? So that gives a lot of potential decision options to the developer. And that has been shown in the field of economics to yield inefficient results, right? So if you provide your customers with too many options, they make bad decisions. So that basically motivates you to build this higher level abstraction of, basically can we hide away all these decisions that developers have to make and offer some either a sky computing vision or multi-cloud vision that is fully automated. Now, what do I mean by that? Just so that we are on the same page. Multi-cloud can be achieved in different ways, right? When it comes to serverless, you can actually have the developer themselves implement this fully on-premise, right? Of course, this is not ideal because this goes against the vision of serverless, that you try to make things fully automated and hands-off for the developer. Alternatively, you can have something called, let's say, a virtual service provider, serverless provider or service provider that aggregates these different underlying serverless offerings and provides the illusion of a unified serverless, just like how an operating system works. Or you can basically have different cloud providers have native APIs that the application would scale seamlessly from developer side. So each of these has advantages. Of course, the last one might appear as crazy, and why would a provider shoot themselves in the foot? But if you think about it long term, the types of applications that this multi-cloud deployment can enable, that would pay the short-term losses. Then the question becomes, why do you want to do multi-cloud serverless, right? So of course, there are many things to leverage. The most obvious one is the pricing differences, right? So this is as of June 3rd, some of the core pricing parameters for AWS Lambda, Azure functions, and IBM Cloud Functions. Of course, there are many details here that are not shown. For instance, for AWS, if you use their own architecture as opposed to x86, you get certain amount of discount and so on and so forth. But at a high level, you see that some core differences might lead to different bills for you, depending on your function. For instance, both Azure and IBM Cloud charge you for at least 100 milliseconds, right? And if your function always happens to be 22 millisecond or 25 millisecond, right? Means that, you're going to get overcharged heavily if you use Azure or IBM as opposed to AWS Lambda, right? This is just one example, but the point being, depending on your use case, pricing might be very different. And it goes beyond just pricing. Memory allocation, if you are expert in these areas, that the memory allocation is different for these different platforms. Resource allocation, scaling of resources is different. Keep life policies are different. Concurrency limits are calculated differently and have different limits. So these are all differences that you can leverage based on your application. And the other interesting thing to leverage is that providers have varying load. So this is the top left figure is from my own paper, where we analyze all the workload of Azure functions, and there is diurnal pattern, and that diurnal pattern can be sensed by the serverless application. Right? A paper later analyzed AWS. They showed that actually, if you measure your own performance frequently, you can see that your performance gets affected by those daily pressures on the provider. So that's very interesting. Recently, this paper came out just, I think, a month ago at the Sesame workshop. They calculated the relative frequency of unexpected cold starts, and you can see a perfect diurnal pattern here. Over the weekends, you don't get many of those, but Mondays or during the day, basically, you get more cold starts, right? So then if you have different cloud regions, right, but based on how your application is getting deployed, you can take advantage of these diurnal patterns that are not necessarily exactly matching in different regions and try to migrate your functions to different regions, right? So this is one possibility to leverage. Of course, quality of service can also be different. As I discussed, you can go ahead and sum up the free tier of different cloud providers. That's the lowest hanging fruit, right? If you're a small scale company. We can also facilitate data deployments. If you have some data in Europe, you have to comply by GDPR. You have some data in Canada. You have a data residency regulation. So instead of bringing the data to one cloud region, you can distribute the compute by bringing functions closer to data varieties, and you don't have to deal with the nightmare of data protection regulation. Now, we discussed that serverless is more amenable than conventional federated clouds because VMs were quite large, actually. The VM images are large, and spinning up a VM takes a lot of time compared to functions. And VMs incur cost even when they're not used, right? So if we have functions that are lightweight, they can quickly be brought up, and they don't incur charge when nothing is being executed. That's the pricing, right? Can we migrate the functions around? To see whether or not that hypothesis is viable, we built some prototype back in 2020 and 21. And we basically, so in this example, I'm not going to get into too many details, but of course, one hairy situation, as you can think right now, is that, what if your data, your primary data is sitting in one cloud? How can you deploy a function in a different cloud, right? So in this example, we kept the data on AWS, but function was being run on both AWS and Google Cloud Functions. And of course, the throughput on the Google Cloud would be lower because data is not local, right? It's remote accesses, but it's still, you can, if you sum up, if you look at the benefits of multi-cloud, you can start seeing the benefits in terms of aggregate concurrency. Same with, dealing with errors. So here, what we did was that we did anomaly injection to one of the clouds, and the system quickly adapted. Once we had some sort of a latency-aware scheduling of events, right? So this is just to demonstrate that this idea makes sense, right? But this was a vision paper, and that was a small prototype. So for the past 18 months to 2 years, we've been working on this other system called Unfastener. And the way it works is that it migrates functions from serverless deployment to alternative execution hosts. This could be VMs, this could be your servers, your laptop. The idea is to reduce costs, okay? So the way it works is that it uses PubSub, right? And it comes with no change to the serverless platform. You don't have to change any scheduler, no load balancer. You just use existing systems that are available, and you can basically have massive cost saving. So we showed that across the applications, we can get up to 90% cost saving with not too much of an overhead on latency. So if you're interested in this area, please read this paper. We're going to present it in a month at ATC. But basically, this is a way we wanted to demonstrate the reality or possibility of migrating functions off a primary serverless. Now, for this case, you're running them on execution hosts, on VMs that are underutilized momentarily. You can think about migrating this to alternative clouds, and that's what we're going to work on next. So if you're interested in these areas, come talk to me. To sum up, we might naturally move towards a multi-cloud serverless future. And considering the differences between providers and complexity of deploying such a scenario, we might need brokers or frameworks to help developers realize this vision. And hopefully through these examples that I showed you, you agree with me that efficient offloading of serverless functions is actually possible if you do it carefully. Thank you for your attention. I'm looking forward to talking with you.
Thanks a lot, Mohammad. Super nice talk. Like the three previous one, this idea is super cool. So we will check your paper. So, okay, so we finished this session with the last talk by Alec. So Alec is, well, the soul of WoSCX, and he's asking a very interesting question. Can WebAssembly create an ideal serverless experience? So Alec, you can go ahead.
Right, I hope you can hear me. So the spoiler alert, it probably yes, but maybe and not today. So what would be that ideal serverless experience? So if we are like thinking from 10,000 feet, what would developers want? So really writing those distributed applications, dealing with scaling and errors and so on is very difficult. So why don't somebody else take care of it? That, I think, is the underlying philosophy of serverless. And if we can push that to the maximum, I think serverless will be really, really successful. So why is it not today? Well, if you are writing code, you would like really not to just write a code like a black box. You have some dependencies you need to think about. You have some inputs you need to take. And it would be really nice if you can write code and see results immediately. So that loop between creating functionality, testing, and then verifying that everything works should be really, really fast. So that's where the WebAssembly really comes into picture, is instead of creating containers and then deploying whole containers, could we deploy a smaller unit of code, exactly piece of code that you compiled, put it there, and then run it. So if we are thinking from like developer experience, as a developer, I would like to write a function. Here's your example. Have that function take some HTTP request and produce some HTTP response, or maybe higher level of abstraction, like in previous talks. You may be having some pub subsystem and you really want to be able to take some events and process them. You do not care if they are coming over HTTP or any other protocol. So you write the function code and then the rest is taken care by the infrastructure. So as we know, today you can do things like that. But how to make it really easy? So Kubernetes is very popular, and you can make it today functions like that, but they are compiled to containers. So can we do it with WebAssembly? So with WebAssembly, hopefully we have that small size, but with small size also come really fast startup time. You only can run what you actually need. If function is really simple, you do not need to include everything and kitchen sink. And then finally, you can do dynamic linking. So function, instead of deploying the whole container, you can just deploy what actually changed, or even you can upgrade if there is security problem or anything like that. Libraries that are used by running functions without changing them. Of course, you want to preserve the old version and do not like destructive replacements, but at least with that level of abstractions, you should be able to do this kind of quick turnaround and security-based modifications. So here I put slides are linked from the website, so I'll be not going here into examples, but WebAssembly is today getting like use cases and getting into all kinds of interesting places, including the really small devices, because you can compile it into really small. And of course, there is a lot of excitement in cloud. You can see, containers are the new normal, WebAssembly is the future. So what is the future if you actually want to run it? So I was experimenting last few months with WebAssembly and Knative. So I will run here a very quick 1-minute demo. So you can get running Knative using just one command. I skip it, we don't want to look on it. Here I create a new directory in which I will be running a function, and there is a template I can apply to create that function. So let's create a function. So there is a command line that creates essentially a little template. You can see that function created here, process some input, generate some output, and just to give you idea, here's just a source code. So all you need to do is to say, you are modifying source code, and you may notice that this function actually not taking HTTP request, and I will be talking a little bit in 1 minute from now about why in background, but here, you are saving it, and then everything that you need to do to run and deploy that function is just run one command, and it will be going in background, so I switch back to slides. Okay, so you may notice that it takes much longer than I was advertising, like a minute or two, because I'm still, when I'm running this demo, I'm actually wrapping WebAssembly into container, and even worse, WebAssembly today has limited support for things like socket and HTTP and so on. So I'm running it with another wrapper like HTTP server, then it is calling actually WebAssembly function. So a lot of wrapping around is going here. And you can find all the details or come and ask me afterwards. And then finally, my thoughts about it is that there is a great potential in WebAssembly if we get it right. Like every technology we can take and make it hard to use or slow or very confusing for users, that really is not difficult to do. To make it easy to use and fast and like Apple likes to say, delightful experience, that takes a lot of work. To make something that is really simple, that's a lot of work involved. So here is the, deployed my function, and here's the function running, hello WoSCX2. And if I wanted to change that function, I would just go to the source code, say again, and boom, I deploy it and should be running. So I think that's all my presentation. I'm not sure with time, but I may be the fastest presenter. Are there any questions? And if not, we will be taking break until next presentations. Thank you. So
Alec, only to say, during the break, I left some poll there about how they like the first session talks. If you want to contribute it, the poll is open. That's all. Thanks.
Right. So I think we will be taking 5-minute break. So we'll be 5 minutes behind our schedule. So, 11:05 to go back. And this is now open forum. Imagine like, if we were in the real conference, this is, we take a break and you can, talk Zoom or Discord or whatever you like. Feel free to use it. And we see each other in 5 minutes. And also, I think you are chairing next session. So if anybody wants to check if their screen sharing and so on works, do it now before presentations.
Yeah, so I don't know if people have already tried. Jesse, do you want to try? Make sure you can share your screen first. Not Jesse, Thomas. Yeah, I'm not sure if people stepped away. Bartosz?
I think I have sharing switched off. It doesn't seem to work for me.
Yeah, so I need to make you co-host. So Bartosz, I'm making you co-host to be able to share screen. And anybody else that want to try?
You can add Tomek as well.
Tomasz, okay.
As co-host. So yes, now I think, yeah, I think I shared my screen.
Okay, I see it and I hear you well. Great.
Okay.
Maciej, do you have screen share rights right now?
Yeah, just a second. I'm connecting with a different computer. Okay.
So during the time, maybe I will try. It's Tomasz, I'm back.
Oh, hi, Thomas.
Hi. Okay, it's working from, yeah.
It's not only for you, but try to go to full screen. We seeing your presenter notes. Now we are seeing brak notatek.
Okay. Okay. Now it should. Okay. Now it should be fine.
Yes, okay, that's good.
It's good.
And-
Okay.
Yeah, yep.
And Pedro posted a poll, right? So if anybody wants, please.
Okay, and yeah, now I can also try. So I need to be a co-host, right?
Yes. So checking, you should be, but if not, let me know.
Not yet.
Who needs to be co-host? Maciej, I think you are.
Maciek, yeah, please.
You're not co-host, I think you are. No, okay, sorry. Okay, try again.
Okay. Yeah. This one, yeah, okay.
I think it worked.
Yeah,
Can you
looks
switch
good.
to the next slide, just to be sure?
Yes, I got it.
Perfect.
Thank you. I stop share.
Yeah, I think the only one that didn't try is Jesse. You there, Jesse? Alec, is Jesse a co-host?
I think I made him
Oh, it
right.
is. Yeah, okay, I can see it too. Yeah, he is. I guess we'll start in 1 minute, right, Alec?
Yes.
Yeah.
Try to see if you can go to full screen.
Yeah, I'm trying. What do you see right now?
Workshop schedule.
Okay, great. Should we start?
I think so. Yes.
Okay. All right. Yeah, welcome everyone. This is the next session, session 2 in WoSCX. The first speaker could not make it here today. So I'm going to play a video for him. Okay, so yeah, Carlos is a PhD student at Imperial College.
Hi, my name is Carlos Segarra, and I'm a third-year PhD student at Imperial College London. In this talk today, I will present our experience gathered over 5 years of using WebAssembly as an isolation mechanism for the cloud. After giving a very brief primer on WebAssembly, I will illustrate the benefits of using WASM as an isolation mechanism through 2 different projects. First, I will cover the usage of WebAssembly to isolate serverless functions in the context of the FASM serverless runtime. Second, I will cover the usage of WebAssembly to replace the thread and process abstractions for scientific applications using MPI and OpenMP. In the interest of time, I won't describe each project in detail. Instead, I will just describe what key benefits of WebAssembly each one utilizes and what benefits therefore unlocks. Lastly, I will outline what are the challenges we think WebAssembly still needs to overcome to become a de facto isolation mechanism for the cloud. So first of all, WebAssembly is a binary instruction format. WebAssembly can be used as an intermediate representation for a variety of programming languages in a CPU-agnostic manner. This is because WebAssembly can be defined as a compilation target in, for example, the LLVM toolchain, meaning that any programming language with an LLVM frontend can be compiled to WebAssembly.
like C, C++, Go, Rust, or Swift. This makes WASM language independent. The design of the binary instruction format makes WebAssembly memory safe. WASM has a very simple memory layout model whereby all WASM state is self-contained in a mutable array of contiguous bytes. Pointers are represented as offsets from 0, and each memory access is bound checked. Offsets are expressed as 32-bit integers, which means that a WebAssembly module is limited to a 4 GB address space, but also means that bound checks can be better implemented using virtual memory and memory page protections. Other pointers, like function pointers, are expressed as indexes in tables, this allowing any kind of sandboxing scale. Most importantly, WebAssembly's memory safety has been formally verified. WASM's design and execution model is platform independent, meaning that the same WASM bytecode can be executed wherever a WASM runtime may be running, be it Intel, ARM, or RISC-V. A WebAssembly isolation unit is also called a WebAssembly module. And note that, again, the WASM runtime and all the different WebAssembly modules live in the same process address space. That being said, WASM isolated code cannot access the host environment, which means that it cannot access the network or the file system or the memory subsystem. WASM provides a standardized system interface, WASI, that defines the API through which WASM modules are to interact with their host environment. Things like memory management, i.e. mmap, may not always require interaction with the host operating system. However, things like file management through fopen, more likely than not, will always require further platform-specific implementation, with, for example, system calls in Linux. Now, I will describe the usage of WebAssembly as an isolation mechanism for serverless. Given its memory safety, isolation guarantees, and language independence, we thought it would be a great candidate. And this is the work we presented with FASM. FASM isolates serverless functions using fastlets, which are WebAssembly modules hardened with C groups and network namespaces. Fastlets can be easily spawned from snapshots of other fastlets by mapping the child's linear memory to the parents with copy and write semantics. Such a mechanism allows FASM to pre-initialize fastlets using proto-fastlets, whereby some initialization code is run on the fastlet, the linear memory is modified, and then another fastlet can be spawned from the modified linear memory, allowing to run some initialization code, for example. The results presented in the paper show that fastlets have considerably lower startup time than Docker containers, and many more fastlets can be packed in the same server, making a much more efficient use of the underlying resources. Additionally, we modified the WASI system interface code to accommodate for serverless needs, making it very easy for functions to communicate and share data between them. This makes distributed ML training in FASM considerably faster and more scalable than with Knative, a state-of-the-art serverless runtime. In summary, using WASM's memory safety, isolation guarantees, and language independence, we can replace VMs or containers for serverless function isolation, thus making a much more efficient use of the underlying resources, reducing cold starts and execution times. We then moved on, moving forward, we were thinking what other benefits of WebAssembly were there at reach to improve existing cloud applications. We realized that WASM's self-contained execution environment and limited interaction with host resources via WASI made it possible to design a very lightweight snapshotting mechanism. We enhanced fastlets with snapshotting capabilities and some other features and named them granules. Granules have the negligible execution overhead, memory safety, and resource efficiency of fastlets, but can also be snapshotted for preemption, live migration, or fault tolerance. Using granules instead of threads and processes, we can make long-running scientific applications using MPI and OpenMP, migratable, elastic, and fault tolerant. This is important because OpenMP and MPI applications, once deployed, cannot be migrated to improve locality, elastically use either resources, or recover from partial failures. In the interest of time, I will cover the details of the technical contributions for which I recommend checking the pre-publication or archive or shooting me an email. Note that this work is still in progress, so we're planning on submitting it later this year. What I will do, though, is I will show a demo of a simple MPI application that, by using granules instead of threads and processes, can be live migrated mid-execution without any changes to the application source code. In this video, I will spawn an MPI application that does just all-to-all communications in a type loop. Originally, as you will see, the MPI application is spawned over 2 different workers. As you see through the logs on the very bottom bit that I will highlight. In the middle of the execution, we will migrate 2 of the ranks that are running in a remote host to the local host. You will see that this very much improves the execution time. The observation is therefore that by making MPI applications migratable, we can benefit from changes in the resource availability in a shared cluster, thus reducing execution time. As you see now, the iteration of the loops are running rather slowly. And eventually, migration will happen. You will also notice that there's a radical difference in execution time between the original iterations and the iterations once all runs are collocated. Again, this is with no changes to the application code. Even though WASM has proven to be a competitive alternative to containers and VMs for serverless functions and threads and processes for OpenMP and MPI, there are still a number of issues that, in our opinion, block its widespread adoption. First of all, WebAssembly has no storage outside of the CPU. In the era of large-scale heterogeneous and disaggregated computing, WASM could be used as a universal execution format to implement a code shipping architecture. However, the existing lack of support to run on heterogeneous devices like GPU or FPGAs challenge this vision. I personally don't think WebAssembly will ever run inside a GPU. Instead, the focus should be making on WASM transparently executable in any kind of wimpy CPU and define well-established system interfaces to access hardware accelerators like GPU through WASI. Second, and in my opinion most importantly, WASM does not have support for hardware-based WASM module isolation. As previously described, WASM modules run in the same process address space, and their safety relies not only on the memory safety of the instruction format, which is formally verified, but also on that of the WASM runtime implementation. Unfortunately, this is not enough security for a true multi-tenant cloud environment, as hypervisor-like hardware isolation is mandatory to isolate functions belonging to different users. There has been an upheaval of research in lightweight hardware isolation mechanisms through hardware memory capabilities or unikernels. These technologies usually compile applications by linking them to a kind of like libOS to run general purpose applications. But maybe WebAssembly and WASI compliant apps could drastically change the landscape of supported applications by opening up the doors of these special purpose hardware isolation mechanisms to generally available applications compiled to WebAssembly. Lastly, WebAssembly has a very active community and a very active set of skillful software engineers from big tech corporations. Things like in WebAssembly threading, support for dynamic language runtimes, or 64-bit WebAssembly are just around the corner and a matter of time. That being said, there's still a lot of space to do research on the application of WebAssembly as a new isolation mechanism for the cloud. Thank you very much for your attention, and I'd very much like to take questions over email or through any other means. Thank you very much.
Okay, yeah, unfortunately, Carlos isn't here, so you can't take questions directly. You can either send an email or post a question on Discord, and he can respond to it there. Move on to our next speaker. Jesse, can you share your screen?
Yep, let me see if it works.
Yep. Yeah, so Jesse is a PhD student and teacher at VU Amsterdam, and he's going to give an interesting talk on serverless and Metaverse.
Just a sec.
Yep. Still there, Jesse?
Yeah, I'm just struggling a little bit with the share screen thingy. Okay, here we go. This should be good. All right, can you see my screen right now?
Yes, I do. Right.
All right, super. Okay, so hi
yeah,
everyone.
Yeah, go ahead.
Yeah. So I prepared this as a 5-minute pitch. So I'll probably be a bit short, but that means that we will probably have some time for some questions. Thanks, Vinod, for the introduction. Indeed, my name is Jesse Donkervliet. I'm a PhD student at Vrije Universiteit Amsterdam, which is in the Netherlands, which is the country that hosts Schiphol, which is a airport that you might know. And I'll be pitching here our project for enabling a metaverse using serverless computing. So metaverse is, of course, a very hot and emerging topic. Perhaps I should say re-emerging topic, because the term has already been around for quite a long time. It actually comes from this book, Snow Crash, published in 1992. So it's by no means a new idea. In science fiction works, of course, you see fantastical representations of this. So you see a couple of examples on the slide over here. I think the most captivating thing that has come out of that in terms of real hardware and software are these VR devices that Apple and Meta are pouring billions of dollars into every year to be the first to try and control the kind of new platform and software ecosystem that will develop around this. But if you look at what we have today in terms of real-world metaverse, then you have to think more about these kinds of systems and ecosystems. So platforms like Minecraft, Roblox, Fortnite pretty much go, or is what as close as we have at the moment to a metaverse. So it's important to understand that these are really not just single games, but really platforms where people get together, socialize. Of course, a lot of it is for entertainment. That's what where these systems started. But they also are increasingly used for a lot of other kinds of things, right? So especially during the pandemic, this got a big boost. So virtual concerts, real world brands opening stores in virtual spaces. We've also seen this, or tried this actually roughly 2 decades ago in Second Life. And we're doing another stab at that right now. So if I would summarize this as sort of integrating further our society into a virtual space to basically do what we're already doing, but increasingly virtual. So these platforms are used for all of these different purposes: commerce, entertainment, education, and so on. Social activism, you see an example here, but they still really don't work in the way that we want them to work, and especially now that they're gathering more attention and growing increasingly large, we are running into these problems of scale and resource management. So you see here a couple of examples: online virtual festivals having canceled because too many people want to join. Same story with this battle on the bottom right. You see a news article about EVE Online, this massive online game, which broke a record in number of players, but then the game itself broke. And so from this perspective, right, I'm coming a bit from the application perspective. This really seems a very good application and use case for serverless computing, because these games are begging for better and simpler scalability and reducing the complexity of the resource management and scheduling. And another sort of good, promising property of serverless in general is that games and virtual platforms like this have highly dynamic workloads. So one moment nobody's there, and another moment everybody's on their lunch break, and they come into your metaverse, so to speak. And we've seen, so on our current project that we've just finished, we've seen that we can use this kind of technology already to improve improve virtual world scalability. So this is a paper we just published at ICDCS, where we use function as a service to do computational offloading, basically. And in this case, we offload specifically compute-intensive parts of the virtual world to serverless functions. And that, combined with some tricks, allows us to improve the number of players, users that we can have in a single virtual space. So the promise is there, and we have evidence that we can already use this for our benefit, but there is also a lot of challenges still around. And I think many of these challenges we've already seen in previous talks today. But this is, again, really coming from the application perspective. So I think games have a super track record in terms of pushing technology forward. So this is kind of my key takeaway for this pitch today is I think maybe we can say serverless has really gone to the next level if we can build a platform or a gaming platform or a metaverse platform using only serverless technology, right? So if we can meet the strict demands from an application like gaming, I think we've come a very long way. So you see here a couple of examples of this: strict latency requirements, long-running processes, intercommunication between processes, high frequency of communication, and so on. So this is a vision, a pitch for a project to build a set platform and game where we distribute a virtual world in really its components that right now are commonly deployed in a single system, and therefore run into a lot of the sort of scaling issues that we know it, and really start to scale them independently and schedule them independently where they are and where we need them. So both scaling and differentiated deployment. So running things on user devices, on the cloud environment, depending on things like latency constraints and so on. So that's our vision, our goal for serverless gaming. So if you find this project interesting or promising, please let me know, and I'd be happy to have a little bit of a discussion about this if there is still time.
Yes, there is time. Yeah, and thank you, Jesse. Very interesting.
Awesome.
Yeah, any questions from the floor?
One question from my side, Jesse. So,
Hi, Pedro. Yeah, go ahead.
Yes, no, your topic is fascinating because I mean, games are really demanding on like latency communication. As you said, there are many things that are breaking the function as a service paradigm, for example. So I think you are doing a nice research, but my question is, do you need, like, are you compatible with any serverless public deployment like containers, or do you need like a new middleware to run this in the cloud?
Yeah, so I think it's a really fair question, because you can take the answer is yes and yes, basically. Yes, we are compatible, but yes, we also need something new, because the sort of simple solution is to just wrap whatever you have now in a container, deploy it on your managed Kubernetes, and call it a day. But I think that although that sort of functionally works, that doesn't really reap the benefits that you would expect from serverless, because you then still lose out on this, well, on things like individually scaling components that need to, for example, right? You only have, okay, I can expand about this later, but I'll cut my answer short to allow further questions, but I could talk more about this, what I mean, if you want.
No, a fast question, rapid one, is that, does your research having to do with actors? Because EVE Online was built on top of an actor framework, and for example, like EVE Online and like Erlang, I think, and other actor frameworks like Orleans that are more stateful and are working in the cloud probably are very designed for this kind of games, it is probably actor framework in the cloud more suitable than serverless?
Yeah, that's also, yeah, so we're also thinking and playing with this, right? And from my perspective, I think that actually these two paradigms are getting closer and closer together. Because we're also the previous couple of talks in the vision papers that you read about serverless, we're trying to expand the boundaries of what serverless means, right? We want to escape this sort of function as a service prison in some sense. If you allow easy inter-function communication, if you remove the runtime constraints and so on, you sort of end up with a serverless actor system. So I think that these paradigms are really starting to grow towards each other. And yes, I think they work excellently for games.
Yeah, all right. Yeah, thank you, Jesse. And thanks for the questions.
Did that answer the question, Pedro? Thanks,
Yes,
Rino.
very good.
Sorry.
Yeah. Yeah, please follow up with any other questions in the Discord channel. Yeah, thanks very much, Jesse. Move on to the next talk. Thomas, can you share your screen? Thomas is an associate professor at AGH University of Science and Technology in Krakow, and also a lecturer at Newcastle. Yep, I see your screen, Thomas, and go ahead.
Yes, it's true. Hello, everyone. I will talk today about serverless edge computing. So thank you for introducing me at the beginning. My area of research is Internet of Things. So simply, okay. So simply in IoT systems, Internet of Things systems, we have the continuum composed of consisting of IoT devices on the lower layer in this kind of system. So smart cars, smart meters, robots, and this kind of equipment. And we have a cloud for computing and processing all the data from the IoT devices. And somewhere between we have edge computing. So this is the layer that we can process the data. We can move some computation from the clouds to the edges to process the data and to increase the response of the system. Nevertheless, the problem is that this kind of solutions are quite complex in architectural design from hardware point of view, because we might have different communication technologies from IoT devices to the edge and from the edge to the clouds. So we might have such technologies like Zigbee, Bluetooth connectivity, mesh networking like open thread communication between the sensors and the edge devices. Then from the edge to the cloud, we might have simple fiber connection, Wi-Fi connection, or we might have low power WAN connectivity like narrowband IoT, which is somehow at some point unreliable for sending the data and with very low throughput. And of course, we might have also IoT devices connected directly to the cloud using narrowband IoT connectivity. So the infrastructure for processing the data in this multi-layered continuum is quite complex. So it's not as easy that we have different components and the fiber connectivity between the components, and that's all, because we have different type of technologies, different type of devices. Then when we talk about the edge computing and the devices, here on the slide, we have some devices from NVIDIA. So we might have enterprise solutions dedicated for some containers located near the BTS stations from the GSM providers in edge computing centers in 5G technologies. Then we might have smaller kind of rack servers with some GPU cards for industrial automation and processing, for example, the streams of video data from the cameras located at the factories. And finally, we might have embedded edge clusters composed of Raspberry Pis, NVIDIA Jetson Nano, and these kind of devices just to process the stream of data in some cafes, shops, small houses, or small factories where we do not need the industrial capacity of processing. So at the end of the day, we have very complex infrastructure with the cloud providers, IoT devices, and different types of edge computing capabilities and different type of devices. So the question is how we can organize the processing of the streams of data, sensor data on this kind of infrastructure. One of the idea is to use concept like osmotic computing, where the services that process the data, called in this nomenclature, in this case, microelements, can migrate and can be moved between some environments, so between clouds, edge, and IoT devices, and trying to self-organize itself to make the number of processing and the trying to self-organize and to adapt to the particular current technical infrastructure between the environments. So in this case, we might think of some sort of slider, but we can move the particles, in this case, services, from the cloud to the edges or to the IoT devices, changing the way and how the data are processed, where the data are processed, and of course, the final quality of processing and the response time of the system. So when we need high responsiveness of the system, we can move all the particles, all the services to the IoT devices. In other case, we can move to the cloud. And of course, implementation of this osmotic computing in real life, in simulation is easy. We have some simulators for osmotic computing, but in a real life, it's quite complex. So let's think of that fog flow pipeline. So it's a sort of graphs representing how the streams data are processed. It's like in a Node-RED solution, probably you know how it works. So the problem is how we can map the services of these data flows to the current infrastructure to process the data. Currently, I'm working on the implementation using Knative way of making a serverless computing. So the idea is to make the processing services as functions in a Knative, which would be driven by eventing, representing the flows between of the data between the processes. So we think that Knative might be way of implementation of this pipeline processing of the stream of data. And of course, the research problem is how we can map the services as a code to the particular devices. So we have to follow some process. First, we need to define the processing, like with the camera, where we have some streams, or video stream. Then we have some services to process this data. So we have to provide this information. Then we have to decompose it to different devices. Then, depending on the available execution environment, we have to prepare some ensembles and deploy on the devices. So it's quite easy when we talk about it. We have some solutions for doing it, and it should be quite okay. But the true problem is that the IoT systems are very dynamic. They have to handle some disturbances that might appear and some failures that might appear in the system. So that's why instead of doing the serverless implementation of this fog flow and osmotic computing, we are trying to handle the problem of adaptability of this kind of systems. So we think that these systems should be adapted to the runtime context, should be resilient to failures, and should have some way of predictive maintenance aspects included in the system. Of course, there are some challenges in this case, how we can assess the quality of processing of in such heterogeneous systems. What techniques and methods can we use to detect the deterioration in the performance of processing in this kind of system? How we can automate the process of self-healing of the system, and can we run these algorithms on resource-constrained IoT devices? Of course, to solve this problem, we have to use some techniques. Till now, we are investigating the reinforcement learning algorithms, where where we have exposed different.
Ja, ik moet wel gaan, man. Dus.
Ik doe even af, dan
Okay, well, probably it's not a question to me. So we have exposed several switches and gauges and sliders from different layers, which were modified and adapted using reinforcement learning algorithms. So as a input, we get some metrics from different layers of the system, and this agent tries to optimize the behavior of the whole infrastructure by rerouting the events between services. Then we thought that we shouldn't have a central agent for the processing, so we need to implement and design the distributed way of communication between autonomic agents deployed at different on different IoT devices, on different edge devices and the cloud. So we think that these nodes should communicate between themselves and try to figure out the common goal for the whole infrastructure, how to adapt to the changes and to the disturbances in the execution environment. And finally, to show some examples of these aspects that this system should handle is use of renewable energy sources. So how to reroute the processing of data streams in the way to use the most of the solar energy as we can provide. So simply we should reroute the video streams to the more sunny edge locations before moving this processing to the cloud. Then we have
Thomas, sorry to interrupt, kind of over time. Can you just wrap up quickly, please? Maybe
yes.
Conclusions.
Yes.
Thank you.
Then the second problem is anomaly detection and detecting how the edge devices deteriorate in the quality. And the last thing is the adaptive monitoring. So we can't expect that we can use the Prometheus to monitor all the IoT devices and edge devices in the field. So we have to optimize the way how we can send the data from IoT devices to assess some failures in the system. And to sum up, we think that to implement the continuum of the cloud edge and IoT systems, we need some sort of adaptability introduced in this kind of systems, but we can't do it without doing out of the lab deployments. So we need to put these devices in the field. We need to, of course, get some requirements for this kind of system from interdisciplinary IoT projects, because it's for application types of projects. And of course, we need collaboration with industrial partners and IoT designers and vendors, because we need to handle some IoT protocols, real life protocols from IoT devices on the market. So this is our view on serverless, adaptive serverless edge computing for IoT systems.
Right. Yeah, thank you so much, Thomas, for the talk. Very interesting and great to see kind of real life applications and use cases here. Yes, we're out of time. So if people have questions, please post them on Discord or on the Zoom chat.
Or offline, via email.
Yes,
yeah.
Yes. Okay. Or email Thomas directly.
Mm-hmm.
Okay. Thank you. I'll move on to the next speaker. Bartosz, can you share your screen? So Bartosz is a associate professor at AGH University in Krakow, a senior lecturer at Center for Computational Medicine, and also involved at the ALICE experiment at CERN. Yep, I see your screen, Bartosz, so go ahead.
Yes, thank you for the introduction. So my name is Bartosz Baryś. I'm from the AGH University in Krakow, and today I will be talking about cloud-native scientific computing. And my background is scientific workflows. This is my main area of interest, and this is going to be my perspective on serverless computing. So just to explain it. Oh, wait a second. Okay, it worked. So I was actually I reworked my motivation slide after the poll this morning. So we have done some experiments with scientific workflows on cloud functions, and the conclusion is that I think it's still valid that cloud functions are not ideal currently for scientific workflows. So factors such as lack of single abstraction that leads to vendor lock-in, or the difficulty of shared state management, which can be done, but also in a proprietary way, or existing quotas limits, they don't help. So I was reflecting on the my answers to the polls from the morning. So I think that maybe the biggest problem today with serverless is the lack of single abstraction. Yes, and in the future that I expect from serverless, so to say, is that it should be the next generation abstraction for cloud applications. That, for example, for me today is Kubernetes, let's say. And really any applications. So maybe my goal here is to highlight some problems that we had with running scientific workflows on Kubernetes. This is the main area that I'm going to show, and with the hope to give some message of what kind of problems should be solved. My slides doesn't cooperate. Okay, sorry for that. So quickly, the scientific workflow management faces many challenges. So scientific workflows are large graphs of tasks that can contain 10K up to maybe 1 million tasks. And there is a lot of parallelism. So we have many parallel tasks that are running, which is a great case for serverless computing. These tasks can be resource intensive, can use diverse resources. And of course, they also we need a shared state, because there is a lot of parallel read-write many type of data access that is happening as this graph is executed. Overall, we can deal with large data footprint, and importantly, scientific workflows typically use legacy software. So behind the scenes, there is some legacy software that we cannot really change to re-implement in a cloud-native way. We can containerize it, but it doesn't solve all the problems. So we have to work around the problems. So, for example, typically this software will expect to read files and will write files as outputs. So we have to deal with that. So the experiments that I will be showing have been done with Hyperflow scientific workflow management system, that project I lead. And let me show some of the execution problems on Kubernetes. So this is the baseline architecture that I show here that we used. So we have the workflow engine that executes the graph of tasks. And when there are tasks ready to be executed, they are submitted to Kubernetes API. And some resources are created on the cluster that execute the tasks. We also use Redis for quick communication between Hyperflow engine and the executors of the tasks on the nodes. And for the shared state management, for exchanging the files between tasks, we actually provision NFS persistent volume. We use ephemeral volumes for intermediate data, and we found it to be by far the best, the most efficient solution, at least on a medium scale, let's say, not on a very large scale. So the naive model of execution would be simply to create one pod or one Kubernetes job for each task of the workflow. So let's start with that. And if we try something like that, we get the result that we got. What is this? So what you see here is a visualization of an execution trace of a montage workflow with 16K tasks. So each row here, dark or light gray, represents a cluster node, and each sub rows here represent parallel tasks. So at the beginning, we have some nice parallelism here, but it quickly breaks down, so nothing is happening. So this is because we simply overload Kubernetes. So Kubernetes doesn't do well with when we try to execute too many pods on it without any queuing mechanism. So not only API gets overloaded, but the scheduler gets overloaded. Kubernetes doesn't do well when it has to manage many pods in the pending state. So it goes to increasingly longer backup waits. And also, if we have very short jobs, then it doesn't help as well, because the pod creation time is about 2 seconds. So if we have jobs that last about the same, then we have excessive overhead for creating the jobs. So a simple improvement of this model would be to cluster tasks. So simply run multiple tasks in a single pod, which can be easily done. And Hyperflow allows for simple configuration of sending of batches. So for example, this says that we should run these tasks in batches of 5, okay? And the result is improved. So we have so in the subplot here, you can see the number of parallel tasks that run in the cluster at a given moment. So the capacity of the cluster seems to be around 120, yes. So we reach this capacity at times, yes. So we have some nice parallelism, but still we have things like this gap here. Oh, sorry. These slides just don't work. I have some timers. So what is this gap? This gap comes from the same reason. So still we have too many pods. The Kubernetes still doesn't handle them. So task clustering can only help to some extent. And then we have come up with a very different execution model using worker pools. So for each parallel task, type of parallel task in the workflow, we deploy a worker pool, which is scalable, which is a deployment in Kubernetes, and auto-scalable using the horizontal pod autoscaler. And it has a separate job queue. Each pool has separate job queue. And this, I don't have a slide with the implementation of it, but under the hood, we use the CADA autoscaler to be able to scale to 0. This is also very important, to scale to 0. We use Prometheus. We use also RabbitMQ for job queues, and we monitor the length of the queues. And then we scale these different pools proportionally to the length of the queues. So maybe there is a quota on the resources for this particular workflow that it may use. So within this quota, all these queues or these pools, will be scaled up or down proportionally to the length of the queues. And the result that we got is very good. So we can see that basically we have a very good cluster utilization all across the workflow execution. This here is expected. This is just a sequential part of the workflow. But whenever we have parallel parts, then the execution is very good. The utilization is as we expect. Yes, so that said, this improved execution model is much more complex than the simple one. So maybe ideally you would like to improve the simple execution model to remove its deficiencies. Otherwise, we have to deal with complexity. But incidentally, this complex execution model is very similar to the implementation, the way it is implemented in Knative. So we look at Knative as promising a single abstraction for serverless computing, and the next step we are working on right now is try to use Knative and evaluate it for large scientific workflows. And there are many concerns that I did not talk about that also should be addressed, but I didn't have time, related to data management, data-aware scheduling, maybe multi-cloud execution, observability, or even cluster-level autoscaling. Okay, thank you.
Great, thanks, Bartosz. Yeah, a very interesting talk, and unfortunately we are kind of out of time and need to move on to the last talk for the session. Yeah, as usual, you can contact Bartosz directly for questions or post in the Discord channel. Right, thanks again, Bartosz. Yeah, Maciej, you can try sharing your screen.
Okay, hello.
Maciej is the director of the San Jose Center for Computational Medicine and also an associate professor at AGH. Yep, and I see your screen, Maciej. Go ahead.
Okay, great. Thank you for this invitation. Good morning, good afternoon, or good evening, everybody. I'm going to tell a bit about my perspective on the scientific applications and some examples of the tools that we developed. Okay, of course, yeah, the background is simple that scientists, researchers never have too much computing power, so there are various ways of trying to get these resources for research, including supercomputers, clusters, even some alternative methods like volunteer computing. And then, of course, cloud and serverless is coming into play. So, of course, we cannot fully replace supercomputers with serverless, but what is interesting is to find, in which cases, which applications are suitable for serverless and how we can improve serverless model to fit broader classes of these applications. So this is what we're trying to do. And some of the examples, I mean, already mentioned by Bartosz in a previous talk, is our scientific workflows. And we did some experiments with cloud functions, serverless containers, getting some really promising results. But of course, this doesn't fit all the scenarios. So especially the cases where we have some long-running jobs in the workflow, and at the same time we have these short-running jobs. So one way is to try find this unified model, as Bartosz was presenting, or another approach is to, which is also quite complex, is to combine different solutions to different tasks. So, for example, running this longer, bigger, fatter, heavier tasks on some containers, even VMs, and then these lightweight tasks that are highly parallel on cloud functions. So this is one option we can consider here. But also there are some examples of applications that need some dedicated user or application specific solutions. And one example we did with our colleagues from CERN is to provide support for data analysis in high energy physics. So they are using their root framework in C++, also with some Python extensions for data analysis. Typically, they run some big loop over the events in their data sets to filter out these interesting events. But the recent extension is our data frame abstraction, which they introduced, and then it allows for running these queries in the higher level format as we are familiar in data science. And there are multiple backends to this data frame, and one that we developed was based on the AWS Lambda. So the functions are used for basically running this kind of map reduce tasks in this whole processing workflow. So it's a kind of similar to Apache Spark, where you have this individual, this high-level description translated into the graph of tasks. And we, yeah, in our experiments, we achieved some good speed up till up to hundreds of concurrent functions. But of course, yeah, depending on the data size, we see that it's not that good when the real data needs to be transferred directly from CERN to Amazon data centers. And because then it becomes, yeah, the data becomes a bottleneck. So we are also now working on some optimizations, caching, transferring part of the data to cloud. So there is an interesting work to continue this. Then another example comes from computational medicine. Yeah, so in our Sano center and yeah, everywhere in this domain, people develop computational models. It can be different types of simulations, like blood flow simulation, represented as an electrical circuit, for example, here. And yeah, the interesting or also computational demanding problem is this VVUQ, verification, validation, uncertainty quantification, when basically we need to run multiple tasks with various parameters to see how the model behaves, how the errors or variations in input influence the outputs, and what is the stability, sensitivity of that. So we developed a cloud VVUQ library based on existing Python EasyVVUQ tool. And also, yeah, there are some classes of models which are nicely fitting. So some of the tasks are quite fast, quite quick, so they can fit into these cloud functions. But on the other hand, yeah, it's also a challenge when we have some bigger models, and then yeah, this cloud functions limitations don't allow to run such big models. So then we need containers and other approaches. And also from the server side, let's say, of the serverless, we did some experiment with extending OpenWhisk for using unused HPC resources. So if we have a big cluster with tens of thousands of cores, and then you have even 1% of it idle, we can actually build out of it a dynamic cluster of OpenWhisk with hundreds of cores on average available. So it required some extension to OpenWhisk to actually dynamically handle this coming and going on and off worker nodes. But then, yeah, the workload is quite dynamic. I mean, the resources are changing dynamically. But then, yeah, we couldn't build an overlay and run this OpenWhisk jobs. And this is especially interesting for some kind of Monte Carlo applications, in which the fault tolerance is quite natural, yeah, because if you even lose some of the jobs, basically nothing happens. You just need to have bigger statistics. Okay, so yeah, in summary, I think that the scientific serverless computing is really an interesting direction. It's not a mainstream, but something quite interesting to explore. And of course, the developments are needed both in the generic frameworks front, like this Hyperflow for workflows, or some generic data analytics frameworks, but also application-specific solutions are important. And this is an interesting also niche, like users are used to their tools. Yeah, so when we provide some serverless backends, we can get some significant speed ups quite easily for them, which is nice for adoption of these models. But also, of course, the challenges of infrastructures and applications also require some server-side developments, like, for example, this HPC WoSCX. So, yeah, there are multiple areas where we work on and try to get some improvements. And yeah, I think that's it. So
Right,
there are
good.
questions, you know, how to find me.
Yes, thank you, Maciej. Actually, we have time for one quick question, if anyone has one. I have a quick one for both you and Bartosz. So a lot of the work you guys are doing are looking at kind of the performance aspects of scientific computing, but there's also an important management aspect of reproducibility and provenance. And I'm wondering if like running on serverless makes that problem harder.
Well, partially, I mean, yeah, it's harder, yeah, because you have to deploy it, and then the infrastructure can be behave differently from day to day, and so on. One good probably side is that yeah, when we have containers, yeah, it somehow enforces the users to containerize the applications, and then yeah, the containers are portable, and then they help, yeah, with reproducibility. So so there are some downsides and advantages, I would say.
Okay. Yeah, fair enough. Always trade-offs.
Yeah.
Thanks, Maciej. Yeah, that concludes session 2 of this workshop. So Alec, are we taking a break before the next one, or just moving right on?
Yeah, let's do 5-minute break. So if bio break and whatnot, and if you are speaker for the next session, I think I already made you co-host, but if you could try right now screen sharing, that would be really great. So let's see. So Alexander.
Oh, sorry. Go ahead. Oh, sorry.
Josep, if you want to try, go ahead.
Yeah, let me try. Let me try.
And Alexander, if you are online, feel also free to try. Yeah, I can see your screen. Do you want to? Yes, now it is full screen. And just try to go to the slide. It's working really good.
Perfect. Good. Good.
Great.
Over to you.
Berend, if you are online, try to.
Yes, I am.
Yeah, so you will be presenting, right? Can you try to do screen sharing of your presentation?
Yes, for sure.
And the same for Alexander Isenko, if you want to try.
This is still the break, right? Sorry, my doorbell.
Yeah, that is still the break. We have 4 minutes, no hurry. I just want, if you have time, to try the screen sharing before we start, the session.
Okay.
Yeah, so I won't be screen sharing, so I won't be presenting, in the sense that I said, because I'm not very sure that my internet is going to be good enough to present, so I'd rather the video play and I can answer questions afterwards.
Okay, are you going to video play, or should I be video playing?
It would be good if you would do it, because I'm not sure if my connection would be good enough to do that.
No problem. Okay.
You see my screen, right?
Yes, Bernard. I think it looks good. Okay, do you want to go to full screen, or this is how you want to? Okay. So I saw it for a second full screen. Okay. And if you move to the next slide. Okay, it seems to be working really well.
Yep. Thank you. And how's my audio? Because my mic, I destroyed it, I think, today.
Well, it always happens exactly like Murphy law.
Yeah.
No, I can hear you. Okay.
Okay.
Little
Thank you.
bit,
I'll be at 6:40, right?
Yeah, in about.
Okay. Thank you.
And Alexander, I will just be trying to play your video in a second.
Yes, perfect. Thanks a lot.
No problem.
My name is Alex, and I'm a fifth-year PhD student.
Let me know, can you hear it?
If you want to scale up. Yeah, so sounds good to me.
All right, perfect. Okay, so like 2 minutes and we will be starting. Okay, so let's get started. This is the last session today. There will be 2 more sessions tomorrow. Please take a look and see polls that we have online. The links are in Zoom chat and they are in Discord. I also think about, if you have any questions or maybe questions you want to ask everybody, ask them in Discord, or, we will have some time also at the end of the workshop tomorrow and also today, if you want to. So let's start with the first speaker, which is Jana Water. However, she cannot join, so I am going to play her presentation video. So let's get it started. Let me know if you cannot hear sound.
Hi, everyone. I'm Jana. I'm a PhD student at Technical University of Munich. And today I'll be talking about distributed systems for graph neural networks. So I will give you a quick introduction, what are graph neural networks, and then I will tell you a little bit about the main concepts of how to make the training process efficient, how to distribute graph neural network training to multiple machines. So first of all, what is a graph? So on the right-hand side, you can see a small example of a social network graph. So here you have something called nodes. You have your persons, and those persons are connected through edges to other persons. So the edges describe the relation between the persons, and the nodes are the persons themselves or the object, depending on what you want to model with your graph. And the nice thing about graphs is they can be found all around us. So not only a social network, but you can also model natural language with a graph. You can model a traffic network or even smaller things such as molecule structures. So there's really a wide range of applications, and that's why a lot of people want to learn on those graphs. So it's quite useful to do that, but you need a specialized machine learning technique, which can take those graphs structured data as an input. And that's why graph neural networks have been developed. And for now, the most important thing to remember is that graph neural networks, they combine message passing. So the nodes send messages to other nodes with neural network operations such as matrix multiplication and things we know from other neural network methods. So coming back to the example with the social network graph, those graphs can become extremely big with billions of nodes and edges when thinking about, for example, a Twitter graph, where you just model the Twitter social network, but also other things. So they can get extremely big and too big to fit on a single machine. That's why we need efficient and distributed training solutions. And in the following, I will present you some main methods. How can we do that? Just to give you an intuition how everything works with graph neural networks. So the first thing, if the graph is too big and you want to distribute it, you will have to divide the graph somehow. So on the right side, you see a picture. There you can see two edges of the input graph are cut in order to obtain two partitions in this case. And then what you do is you distribute the partitions among the machines, and then you train your graph neural networks on those machines. But the question is, I mean, all of those edges are kind of important to the graph. So how do we partition the graph now? Which edges do we cut, or do we, for example, cut some of the nodes? You can also do that. What do we do if some information is lost, and yeah, maybe some new communication between the machines arises like that? This is what the first concept, partitioning, is all about. And then the second part, something also quite unique to graph neural network training, is called sampling. So as I said, training on the full graph is not really doable. So there's a solution that you only train on a subset of the nodes. You can see it on the right side, that you only train on the colored nodes here, and you just leave out the rest of the nodes in order to obtain your final model. But now, yeah, the question again is, how do we choose which nodes to include? How do we choose the nodes containing the most information, the most important information? And that's what sampling is about. So there are many different strategies out there. You can just sample randomly. So you say, okay, I just sample, let's say, 10 neighbors of a target node. But there are also more sophisticated methods where you take the previously sampled nodes into account, or you will first form subgraphs and then you sample within those subgraphs. So there are a lot of strategies which you can use to do the sampling step. And now something which I also found interesting is serverless GNN training. So the goal here is to improve the scalability at a low cost. In this example paper by Thorpe, and what they are doing is they divide the training step into fine-grained tasks. And then depending on the task type and the type of data which is used within the task, they either perform the task on CPU instances. So here in this example, they are using EC2 graph servers. And then there are other task types, for instance, here where they process tensor data, for example, the features of the that they use within the graph neural network training process. And there they are using Lambda threads. And like this, they say, okay, they improve the scalability, they can scale out and scale up how much they want to, but at a low cost here. That's what they are doing. And a paper that I also want to highlight here, because that was like the first paper I found that we're doing serverless GNN training. Yeah, and then there are not only those strategies that you can do, there's also, for example, scheduling, something quite common when you're using a distributed setting. Then the type of parallelism. So when you train neural networks, you can have the data parallelism, where you have your data points parallel, but you can also split up the model, which is then model parallelism. Then other things you can take into account is the synchronization mode. Are you working in a synchronous or asynchronous or maybe even hybrid setting? And another question is, how do I propagate the messages between the machines? Do I use a push or pull-based approach, for example? So as you can see, there are many other strategies out there, which yeah, just doesn't fit in the scope of this little talk here. That's why I will recommend you reading our paper, which was published this year, where we investigate those strategies in detail and also compare different strategies. So if you're interested in that, please check out our paper. And yeah, if you have any more questions, feel free to reach out to me anytime.
Okay. So let's move to the next talk. Alexander, I will be playing your talk, right?
Yes, thanks a lot.
No problem. Again, let me know if you do not hear the sound or anything like problems like that shows up.
Hi, my name is Alex, and I'm a fifth-year PhD student from the TU Munich. So currently, I'm focusing on ML systems research, and today I'm going to be presenting a submitted preprint of my current work, which is titled, How Can We Train Deep Learning Models Across Clouds and Continents? So first, a little bit of an introduction. As we all know, training deep learning models is expensive because the accelerators themselves are expensive. If you want to scale up, meaning either faster training or training bigger models, we need a high bandwidth interconnect between the accelerators due to how much data needs to be shared between them. However, if we could reduce the bandwidth requirements to around 1 gigabit per second, this would actually enable us to use accelerators that aren't necessarily close together, such as in different data centers or even by training over the internet. Additionally, with the current cloud computing landscape, there is an option to rent VMs with so-called spot prices, meaning that you pay up to 90% less, but these VMs can be interrupted at any time, basically meaning whenever another customer is willing to pay the price, the full on-demand price. Also, the availability and cost of slightly older GPUs is currently much better compared to more popular GPUs, such as the T4, which is around 30 times cheaper than a 8 times V100 node. And adding to that, if we could use different cloud providers, we could leverage their individual capacity, which may differ from region to region or even the time of day when you book the VM. So, summarizing, if we could bring down bandwidth requirements, use slightly older but far cheaper GPUs, and leverage multiple hyperscalers, in theory, we could train much more cost efficiently. And what we did is we actually evaluated exactly this scenario. So we met at work with by using HiveMind, which is a framework that enables training in low bandwidth scenarios, so typically less than 1 gigabit per second. And it was initially created for collaborative deep learning. So while there is some research already on how using it with spot-priced VMs, it was actually never analyzed under the cost efficiency or multi-cloud aspects. So therefore, what we did, we started off with a model suitability study with CV and NLP models with varying parameter sizes. So we tried 12 million to 560 million parameters. We checked out how geo-distribution affects the training progress and the cost as well by training on up to 4 continents at the same time. So we did the US, EU, Asia, and Australia, all with different hardware distributions to perfectly be able to pinpoint if we add one GPU in one particular continent, how does it affect the throughput? And we also evaluated the multi-cloud aspects of it. So we trained on Google Cloud, AWS, and Azure all at the same time. And finally, we evaluate the hybrid cloud setups as well, but where we combine our on-premise hardware with remote and local cloud resources, meaning on the same continent or not on the same continent, and with some of them even having a very low bandwidth of around 500 Mbits and a round trip time of 5 milliseconds. So what were the results? So what we actually managed to achieve is to create 2 new cost-efficient training setups when compared to fully centralized training. So this figure shows the spot price DGX2 node in the center, which costs around $4 per 1 million process sample. So this is the x-axis, and it reached a throughput of around 400 samples per second, which is the y-axis. This means that everything to the left of the vertical bar was cheaper, and everything above the horizontal bar was faster than this hardware setup. And there we can actually introduce 2 new setups. So we circle the T4 and the A10 runs with 8 GPUs each. Both are cheaper at around $2 per 1 million samples, while the A10 is also much faster than the DGX2 run. So while the A10 is obviously kind of better on the first look, right? It was actually run on Lambda Labs, which is a cloud provider that has a very, very competitive GPU pricing and doesn't incur any network costs. While the T4 experiments were actually run on Google Cloud, which has additional network costs. And surprisingly to us, it was actually still cheaper than the A10 runs. So yeah, definitely check out the paper for the evaluation on how network costs could be the most significant part of the final bill when training in such a distributed environment. Also, we found out that the small models can still be scaled with more GPUs. So the current research argues that big models are easily scalable due to having very slow training grounds. But in our case, we actually show that models with even 12 million parameters can still be scaled with 8 or even more GPUs. So the figures that you see here on the x-axis, you see the GPUs, so increasing GPU amounts, and on the y-axis, you see the different throughputs. And to the left are the CV models, and to the right are the NLP models. And hopefully it's kind of clear that all of them more or less scale, and the bigger the model sizes get, the slower the speed up, but it's only in absolute values here. So you like the small models look better than the bigger ones, but in relative cases, they are actually all the same. What we also found out is multi-cloud just generally works. You're only bound by bandwidth and cost limitations. So yeah, it's perfectly possible to do that. And hybrid cloud can work, but we found out that it might actually be more cost efficient to actually only use cloud resources if bandwidth is very limited, as it was in our case. So yeah, this is actually it. Thank you very much for your time. So please read our paper or send us an email if you have any follow-up questions.
So are there any questions? We have time to Alexander. I have actually one quick question, Alexander, if you...
Sure.
Do you know Berkeley Sky Computing? Did you look on what they are doing, especially for training multiple clouds GPUs?
Do you mean SkyPilot by any chance?
SkyPilot, yes. I mean, they have a whole bunch of projects.
Yes, exactly. So I'm actually citing them as well in kind of like my future work. My future work basically, and the related work as well. So I'm very unfortunately, I only noticed that project just before I was prepared to submit the paper. So I couldn't start off with that when I started the work. But yeah, I'm actually very, very interested in like using their project to kind of leverage their APIs to make it work, because I feel there's a lot of potential there to kind of combine the work that I did with their work, and to, yeah, if we could make that work, that would enable a lot of potential basically.
IBM is one of sponsors of that Skylab, and we actually have some people from IBM working there. So yeah, I think it is very interesting.
Cool. Yeah, so I'm visiting in June to September. So I'm visiting IBM Watson in the US. So maybe we can work there on that.
Oh yeah, definitely.
Yeah.
Okay, the next, are there any other questions? If not, we can go to the next speaker. Is it Josep or Josep? How do you say?
Josep. It's Josep.
Josep.
So let me share the screen. Can you see it well?
I can see your screen. It looks very good. And
you look you can use my face also. Okay.
And I can hear you. Yes.
Okay. At least you can hear me. Okay. So hello everyone. I'm Josep Lluís Berral. I'm from BSc and the Universitat Politècnica of Catalonia. I will talk about AI-based containerized edge cloud orchestration. This is basically learning from workloads for smart provisioning. So in this short talk, I will explain a little bit the different interests that we have in our research, what we're trying to do, the reasons and the motivations, and also a little bit of what we have achieved or what we are experimenting right now, and the next challenge that we have, or the different fronts that are open in this topic. So basically, we're doing smart provisioning for AI, so AI for cloud edge. The idea is that we want to do dynamic orchestration. We have workloads like containerization, virtual machines, but now the next step is the logic step, and the natural step is going to serverless, one of the natural steps, and we want to do this smart provisioning. Basically, what we're leveraging is machine learning. People say AI, but it's actually machine learning, statistical learning, and statistical methods. Because the idea is that we have to do placement and provisioning of workloads, either in the cloud or in the edge. And these workloads, they have patterns and statistical properties that we want to leverage or we want to advance during the execution in order to place them correctly and not just at random or just based on some dumb information that we got from the latest steps, seconds, or minutes. And what we do is workload characterization. That I will explain in a moment. And also this for the scenario is in the cloud to the edge. We were focusing a lot on cloud recently, but now we know that cloud is moving to the edge in order to leverage the fact that we are near the users, near the data, that we have amortized resources there to reduce latencies and also to save some privacy in the process. But we know that every decision that we have to make must be automated. And if these decisions are kind of smart, let's say, they have some process, we have to be able to automate these. And this is basically what machine learning does at the end with a little bit of engineering over it. And we have to deal with hyperdistribution. What if everything is distributed? What if we cannot see the full picture at once? So basically, smart provisioning. As I said, we have containers, virtual machines, microfunctions, Lambda, blah, 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 lot of things that at the end, it's workloads that we need to place. So we need to optimize cloud and edge and the resources for them because we have lots of users competing for the resources. We know that resources cost money or cost energy or cost credits or they cost basically. And what we want to do is to say, well, let's manage them properly, that we are not wasting resources for this. Maybe we want to consolidate things. We want to put as many applications in the least as possible resources to save energy, to save money, etc. But for this, we have to know our applications. We cannot just compress everything together in a single place or put things in a place where they don't fit, where we don't have resources, enough resources for them to work properly. And we use knowledge discovery. This is basically data mining, modeling, knowledge discovery by itself of modeling, prediction, and forecasting. So the idea is that we have lots of workloads and they have complex and hidden patterns. Hidden meaning that they cannot be seen at single sight. We have to look at different scales of time or of size of resources to start to see things. And what we'll want to look is for characteristics, things that tell us, well, this application will behave this way or this other. Will it repeat? Will it be recurrent? Will it be usual? And from this, what can be derived and predictable? If I see an application and I can tailor it or I can model it and characterize it, I will know how it will behave. And the next time that it comes to my system, I will say, well, I know where to place you without having any surprise. That you will not demand me this or that I will not expect. And for this, we use machine learning models. Basically, we get some data from the past or data from the current running system, and we create a statistical model that is able to forecast things or to make predictions. But we must be aware that this must be simple because we don't want to spend our time, all the resources that we save and all the time that we save from wise or smart orchestration, we don't want to waste it doing predictions or training models or doing inferences in models. We want something simple, something that's fast, and something that's more useful than accurate. In most of these scenarios, we have found that we don't need to go to the most accurate model in the world. We don't need to go to the 0.95% accuracy. Well, 95% accuracy. Sometimes quick and fast and silly models are enough for us to have a decision where to place a workload or not. And that's what we are looking for. So for this, we get some traces from the system, telemetry, from the applications, from the system, from the users. We characterize them to see if there any pattern that they can use when scheduling this application. And we make good choices, or we try to make good choices. And this in an environment that's from cloud to edge, from billion users and applications in the cloud to now billion users and applications or potential also in the edge. The human cannot handle everything of this. We want to be able to make this dynamic, adapt, and updatable, that this means that we cannot have a person tuning every application, tuning every device. We need something that's able to run and do the job for us of modeling this. So basically, that's the thing. Training fast, running fast, and updating fast. Right? The good models that are small enough and lightweight enough to do this. Also, in distributed environments, what happens if our knowledge is distributed? If our application is distributed, I need the telemetry from every place. Can I do models in every local device and then put them together? So this is basically our interest. Characterize the application and systems to try to improve these decision makers, where do we place an application or how many resources we give to it. And then, well, do this provisioning. At this time, what we have been done in the recent years, it's basically mining the behavior from workloads, try to find recurrent things or things that we can observe automatically from workloads in order to make decisions, trying to detect common patterns, and now I will explain some next steps that we have on open fronts. At the beginning, this work with IBM Watson, 2020, this is the oldest one, we made automatic pattern discovery. We had a method in which if we get a trace from a containerized, in this case, application for cloud systems, can we identify common behaviors? Common behaviors does not mean to learn a trace or learn that it is going just up or down, meaning that in a given segment of time, the application will have some specific behavior that I will see replicated along its execution or in next executions. And how can I exploit that? How can I get some statistics from these? What if I detect some phases, some specific behaviors, and I can extract this statistic information and know that, well, now I will have high variance or low variance, or now I will have stepwise behavior, or I detect a periodic behavior that will repeat for long. This is one of the things that we do using different machine learning techniques and also statistical learning techniques like autoencoders. In this case, CRVMs. It's a let's say mechanism for autoencoding and also clustering for this. Then we went to common behaviors. What if we find a common behavior, like, for example, stationary behavior, meaning that, okay, we have variance, but we never move from the place. Oh, the part. Later, periodic, what if something repeats or something that's trending? We apply the method here, or we created a method called theta-scan, trying to discover if something repeated automatically across time, and if not, if this was because it was stationary or trending, or it had just a big step on behavior. So if we know that it repeats or it has no repetition, then we just can start counting on this behavior for the rest of the execution. So we know how to allocate it and which resources to give it. And now the recent work, 2023, we are trying new methods for new methods like transformers in order to detect or to discover, well, not discover, to detect specific behaviors. Like, for example, what if I have a sudden burst of resources? For this, we are using these new methods, and so we will have good results, I hope. So, next challenges, novel architectures. We are trying to look what happens if we apply RISC-V for this new kind of hardware, new kinds of accelerators, GPU, TPU, and something that comes next. What happens if we have fairy tale learning? What happens if our workload is distributed? And new kind of applications, new kind of decision-making mechanism, new kind of schedulers that are compatible with what we are doing. Here's the bibliography. I will share the slides, and you will be able to read them from the work we did. And this is the slide of the logos of the different projects that we are collaborating with and that are in the orbit of CloudStars in some point or another. So thank you very much. And if you have any question, you can ask me or contact me or just tell me.
Yeah, and feel free to post questions in Discord, and also share the slides in the Discord for people if you are going too fast. Berend, you are the last of speaker for today. Are you ready to share your screen?
Yes, most definitely.
So you will be talking about AI, edge, cloud, everything together.
Yes. You see the screen, right?
Yes, I can see the screen and I can hear you very well. Thank you.
Okay. Good afternoon, everyone. I'm Berend Gooit from Nearby Computing, currently doing a PhD at UPC of Barcelona. Today I'll present a summary on machine learning of our cloud edge machine learning deployments. So we combine cloud infrastructure with edge devices for real-time capabilities. And we use machine learning and cloud edge to optimize the performance, efficiency, reliability, predicting workload demands, and efficient utilization. You can also identify security threats. So the benefits of using machine learning and cloud edge is basically it unlocks performance, scalability, and cost efficiency. So let's explore specific applications and benefits of machine learning in cloud edge environments. So this is basically a short introduction to our Nearby One's research on optimizing resource allocation in edge environments. So first off, I'll talk about what's cloud orchestration, then a high-level overview of machine learning orchestration in the cloud, and then I'll present a taxonomy of all the research directions on this topic. Then I introduce our product, the Nearby One orchestrator. Then going into some special features we have, and give an example of how we do machine learning orchestration in Nearby One, and wrap it up with a conclusion. So cloud computing has become the mainstream industrial computing paradigm. It offers scalability, cost efficiency, and utilization of virtual technologies. And cloud edge service providers use virtual machines and containers for automated application deployment. So now we focus currently on container orchestration, which is used to manage containerized applications. So it includes tasks like resource allocation, deployment, autoscaling, and monitoring. So there is this need building for enhanced orchestration systems, because traditional orchestration systems they lack adaptability, scalability, and consideration of very heterogeneous workloads, whilst respecting quality of service requirements. So here on the right in the figure, you can see an overview of machine learning based orchestration of containers. So you have application workloads, compute cluster, the infrastructure, and some kind of optimization engine, which is based on machine learning. So to start off with the application workloads, which you can see on the left, the users request submit application workloads to the orchestrator, and they have certain quality of service and resource requirements. Then you have the compute cluster, which is a group of virtual physical computational nodes in a shared network, which could be data centers with fog nodes and edge nodes. And the responsibilities, well, it could include like allocation, scheduling, scaling, migration, etc. And then the infrastructure, which could be private clouds for exclusive resource sharing within organizations, but also, of course, public clouds and fog and edge infrastructures for, reducing latency and energy consumption. And on top, we have the machine learning based optimization engine, which typically exists of a workload modeler, a performance analyzer. Those two get combined into a predictor, and then finally another decision maker, which could be machine learning based or heuristics based. So the machine learning orchestration is quite large. It has many different topics, including architecture, infrastructure, objectives, predictions, and provisioning. So I'll shortly go through them and then focus on a singular part, which we are working on ourselves. So in architecture, yeah, you had in the past a monolithic architecture, which is of course outdated now. Everything is shifting towards microservices and serverless paradigm, where microservices addresses the scalability and maintenance challenges by splitting the applications. Then infrastructure already explained in the previous slide. And objectives, well, there are 4 main objectives in the literature, which is the resource efficiency, energy efficiency, aims to minimize the electricity consumption, cost efficiency, of course, minimize financial cost, and service level agreement assurance is also a well researched goal. Then for predictions, you mainly have the workload predictions, methods to analyze the performance on hierarchical scale, anomaly detection, and dependency analysis between microservices, for example, or serverless functions. For resource provisioning, which is basically the decision maker for scheduling, scaling, be it horizontal or vertical, or migration of services. So this is a high-level overview of all the research being done in orchestration with machine learning. And of course, yeah, depends. Then introducing our own orchestrator, which is basically our product. It's an end-to-end cross-domain orchestration platform for latency-sensitive, data-intensive, and mission-critical applications. It solves the telco and enterprise challenges in workload deployment, because it manages distributed systems, networks, and applications from edge to the cloud, and adheres to industry standards from CERA, which is the Converged Edge Reference Architecture, and it's an edge orchestrator operating globally from edge to corporate data centers and public cloud. And all of this can be managed from a single pane of glass interface for rapid provisioning and resource allocation. So on the bottom right figure, you can see it connects the infrastructure, network, and applications for sophisticated orchestration. And Nearby One is in the center, the manager of all of these 3 areas, which in its turn enables higher performance and efficiency by integrating these components. Also, it's vendor agnostic, so it's a solution for flexible deployments. It has already been tested with leading vendors across edge tech layers, especially in Europe. And it's a comprehensive edge orchestration and for the market, including Internet of Things, fog computing, multi-edge access computing, 4G and 5G networks. So let's move on to our features. On the right is a display of our internode orchestration. Internode meaning orchestration of multiple clouds. And then we also have orchestration of the clouds themselves, which is called intra-node orchestration. So in this figure is just a display of how the master machine learning model instructs the slave machine learning models, which we could call hierarchical or machine learning. And this can potentially go all the way to the edge devices in the near future. So thereby we go beyond traditional orchestration to tackle complex challenges in edge computing with dynamic resource allocation, real-time monitoring, leveraging, and we leverage existing tools to on top of market. So we have a really flexible and open architecture, and we integrate seamlessly with existing systems, which are customizable to unique requirements. So let's keep it short. I'll just give a really specific example of what we are doing now at Nearby Computing. So this example shows the role of machine learning in intercloud orchestration, how it leads to improved autoscaling and a green label for your edge cloud network. So on the top left, we have our product, the AI orchestrator, which from where we gather CPU and memory usage, but also network traffic, disk I/O rate, historical patterns, and environmental factors, energy usage. And based on these models, we use machine learning models to analyze this data. On the top right, we analyze the historical patterns, and we make some predictions, which are displayed in red. So in this case, we were predicting average CPU usage and average memory usage. And then with those predictions, we can move on to predictive autoscaling. So we insert with a delta t time window, insert those predictions in the current existing systems, and that in that way the cluster is already completely up to speed before the probable workloads arrive. So this is dynamically scaling the resources based on prediction, and this ensures optimal performance and avoids over or under provisioning. And that under or over provisioning results in energy efficiency. So optimized resource utilization reduces energy consumption and the avoidance of idle infrastructure. So therefore, we have our edge cloud network. Hopefully, we will get to that green label. We couldn't reinforce the positive impact on resource allocation, energy efficiency, and the environment.
Hi, Bernard, you are over your time. Okay, conclusion. So
conclusion. So machine learning orchestration has a wide range of techniques and directions. We have intelligent algorithms for edge cloud orchestration. We do this on hierarchical levels. I provided a specific example of what we are working on right now. And just to show the significance of this, it is predicted by Andrea that in 2030, data centers will use 3,000 terawatt hours of energy. The Hiroshima nuclear bomb was 0.0175 terawatt hours. So that's approximately 171 million bombs, which is in 2030 will be 5.5 Hiroshima bombs per second. And that's for data centers only. So imagine if we add the fog and the edge to this. So in this way, we are contributing to energy reduction of these cloud edge systems. Thank you.
Thank you, Berend. So that concludes today's workshop. We will continue tomorrow. So I hope to see you, and we will have more talks. The tomorrow workshop will be shorter, only I think 10 or maybe less than 10 talks. And we will have some extra time also at the end of the tomorrow workshop for questions or discussions if you want to bring any topics. And I think Pedro have those very interesting poll results showing like the cloud, how they change the topics between WoSCX1 and WoSCX2. Pedro, can you show them, like screen sharing? Oh, I see. Yes. Okay. I can see your screen right now. So the results are in Discord channel, and we will see. Pedro, if you want, I can try to share it if you have problems. Can you hear us, Pedro? Okay, let's then do it. Okay, you're trying again. Okay. We can see your screen now. Make it bigger. If you are speaking, you are on mute.
Yes, I think now you should hear me. Sorry. Okay, so this is the first question that we did. We repeated the questions in WoSCX2. So as you see here in the what are the main challenges, we see bigger responses when they are repeated. So state, latency, programming abstraction, security, and transparency are like the major questions, but we see here a lot of interesting questions. We have 36 answers, and we see lack of SLAs, performance variability. We see debugging that we will repeat now. The same question was X1, middleware integration, cost and pricing, data management, and application topologies. This is this year. If we compare this to the result for the past year, then we see looking it in the other screen. So here now you see this is the previous questions. So this was WoSCX1 some months ago, and state was also in the top of the list. So state has not been solved in serverless computing. We also hear billing cost is also the same problem. Low latency was also there. We haven't advanced much, I see. Then debugging was bigger. Now debugging is smaller, but I'm not sure if we advanced a lot in debugging. And then ultra scale and complexity. Then another question that we did, the second one was about the future of serverless computing. And then in the future of serverless computing, let me now move this window here. So then this was the second question, what is the future of serverless computing? It is interesting that they put everywhere, like serverless everywhere. Serverless in the edge, serverless in the cloud, serverless for AI. It's like single abstraction is interesting also, multi-cloud. And then we see smaller than big functions, AI, artificial intelligence, AI integration, then LLMs here. We still see here multi-architecture for automation, edge, and general for serverless and serverless GPT. Then if we look at the commonalities with the last year, the WoSCX1 future of serverless, then you see here, so we can see both. This is future. So in future, we have hybrid, cloud continuum, edge, distributed function as a service, service composition. So cloud continuum now, this in the second one, in future now it's not top. So we don't see any cloud continuum this year, but we still see edge. So probably we have even more information in this second workshop because we have more answers, but 33 in front of 20 that we had before. So like summaries everywhere, like this is shared in both chats. Some problems still are remaining, like the state, like latency imperformance, like programming abstractions, like debuggability. And in challenges, we are seeing here the emergence of AI and serverless GPT and LLMs, like a new concept that we didn't discover in the previous workshop. I think these are mainly the conclusions that we can get from these polls.
And just to be clear, when you show the white, which is right now, this is WoSCX2, which is right now.
Exactly, WoSCX2 is white.
Good. So we will continue tomorrow. That will be shorter session. Hopefully everybody can come back. And if there are any questions, yeah, this is now open mic forum finishing. If somebody wants to bring up something, feel free to do it. If not, you have another opportunity tomorrow, so no worry. Okay, thank you. I will be finishing recording, so stopping recording right now.